Hi everyone, let's take a look at midterm number 2. There were two versions of this test, 21 and 22. I'll show you the 21, and when there's a difference, I'll show you the answer in 22. All right, so first question. Okay, now a couple of folks tried to do this with a slice and latch, a couple of folks tried to do this with an ICE grade, which works, okay, but it's kind of the longer way to do it. If you recognize that it's, it says there in big friendly letters, buffer, yeah, you just use the Henderson-Hasselbalch equation. So that's what I did. Remember, the Henderson-Hasselbalch equation is designed for medical students to answer buffer questions. All right, so it's a good shortcut. All right, so there's the Henderson-Hasselbalch equation, right? And it says what mass of sodium benzoate, which is the conjugate, right, should be added to 0.75 molar of benzoic acid, which is the weak acid. And those are those features in the Henderson-Hasselbalch, right? So I think one or two of you have got the fraction upside down, which would change the sign, right? But like, if you use the one in the back, that's the one in the back, all right? So be careful, just use the one in the data sheet, right? So if you like, we've got to figure out concentration of this guy, and then we can figure out grams molecular weight moles, right? This is given, okay? These guys can be either given or determined, right? So we see the pH has to be 4.75 for the buffer, and the Ka of this thing is 6.5 times 10 to the minus 5. So, if we list our variables, we have everything we need, all right, when we turn Ka into pKa. That's what I did here. Okay, all right, so then we go through. All right, so just basically plug and chug. pH, pKa. I didn't change this yet, just kind of insert those. You can throw it all in at once if you want, all right? And you just go through and you solve for, essentially, at the end of the day, the concentration of the conjugate, right? Which was, on this one, 2.8 moles per liter. On the other one, real quick, it was 1.9 moles per liter. Okay, it's the same math, right? Okay. Once you've got the concentration, well, hey, moles is CV. Oh, nice for me, 1 liter, so it's 2.8 moles. And, over there, 1.9 moles, right? And then, hey, moles times molecular weight, you can work out the molecular weight of this is grams, 397, and 270 for the other one. Okay? All right. Now, is it better resisting changes in pH? Kathy gave me a generic definition of what a buffer does. That wasn't the question. All right. How do you know if something's better at resisting H plus or OH minus? Well, it depends on the ratio of conjugate base to weak acid, right? Okay. Because when we look at the numbers, there was more conjugate base in both examples. This equilibrium, if there's more of this, it will suck up H plus and turn it into here. More, if you like, right? Okay, because there's more of it. Okay, so that's the ratio of conjugate acid to base in the buffer system. That tells you if it's more good, if it's, has a buffering capacity more geared towards H plus or OH minus removal. Okay. All right. Next one, a couple of ways you could do it. So weak base coffee. If you ever drink a really strong cup of coffee, sometimes there are consequences, right? Okay, so, weak coffee is actually a little bit acidic, not necessarily because of the caffeine that's in it, but other things. But looking at caffeine by itself, there it is. It is a molecule with nitrogen, so it's going to have lone pairs. It's going to be a weak base. And it's a super weak base, all right? Okay, so actually it's a stronger, weak acid, but we know we're talking about bases, right? Okay, so I did ask you to work out pKa. Now, obviously you could use either Ka, Kb as Kw, go from there, or pKw as pKa plus pKb. Either version's fine. I think I did, the pKa version here, and then on the other one I did the Ka version. So, just freeze out whichever one you went for, all right? Okay, now, so a really strong cup of coffee has about 425 milligrams per liter, yeah? And this is, we did have Kb up here, so it's going to be a base, yeah? Okay, you could have flipped the equation and done it as an acid if you wanted to, but it's, it was set up as a base, all right? So I think most of you did the base one, all right? Okay, so there's my caffeine, all right? There's water, conjugate acid, OH minus, so that's how a base reacts, yeah? So I worked out down the side here, if I got 425 milligrams, turn it into moles per liter, 2.2 times 10 to the minus 3 for that one, 1.93 times 10 to the minus 3 for 22. Okay, then because you have the concentration, you can just do your standard ICE. There we go. weak-based approximation is fine. A couple of you didn't do the weak-based approximation, gave yourself more work, but same answer, doesn't matter. Okay, you can, rule of thumb is always do the weak acid or weak-base approximation. All right, so, just rearrange it, the usual thing. Now, X, of course, is the hydroxide concentration. Once you've got the hydroxide concentration, you can turn it into POH, pH in the usual way. Okay, so 7.5 for that one. So, caffeine itself is slightly basic, right? Okay, here 7.4, again freeze to get details, 7.4, and you can see where the point, obviously you can see where the points were awarded. Okay. Question 3, we had a weak base, that was the harder one. Weak acid, slightly nicer question. I think pretty much everybody got this one, which is nice. So, weak acid, find Ka, we did this one in class essentially, right? So just change the numbers. There's your grid. I'm given the pH and the concentration, I can find Ka. So pH is minus log of H plus ion. Rearrange to find pH, rearrange to find H. I'm given pH, I find H plus ion concentration, which is X. Stick X in, Ka expression, get Ka. I think, very good. And then, hey, percent ionization is H plus over HA times 100, and it's actually a small percent associated. The other one, different numbers. Same procedure. So 1.58 times 10 to the minus 4 was the concentration. 6.66 times 10 to the minus 8 was K. And then 0.042%. Okay. Question 4, the easy question. Okay. So just the concentration, just the pH of various things with the same concentration. Trick was, recognize these were strong reagents, assume complete dissociation. So, what you see is what you get. So 0.0045 H plus, that pH, right? Now, some people didn't recognize that was an OH minus, right? And there was 2 per unit, so the concentration was twice that. And then you find OH concentration, so you find POH and then H plus pH, right? Here, acetic acid. Hopefully you're familiar with the whole setup for that, 3.5. And here, base, same but with a twist at the end, you find POH and then pH, okay? So those are the numbers, all right? Actually, I think on the other one I had the grade scheme's actually on the other one. So there's the other one, just to go through it, it's the same, really. So 0.0065, 2.2, 12.1, 3.5, and 11.2. The numbers are very, very close, of course, because the concentrations are similar, but they're not the same. Okay, so be careful. All right. Finally, same for everybody. This one was, gave you a bit of a hint, didn't I, when we talked about it in the video. So, I think I did magnesium hydroxide. This is manganese hydroxide. So KSP, calculate the pH of a saturated solution of manganese hydroxide. KSP is 1.9 10 to the minus 13. So obviously, there's our balanced equation. The key is you get 2 OHs, right? And KSP is MnOH squared because there's 2, right? Okay. Set it up. Now, if you think about it, some people did S, which is fine. That's kind of what the book does. I just use X, right? So X or S. So I've got concentration of Mn is X, concentration of OH, because there's 2 of them, is 2X, right? So squared. I get an expression for X in terms of this KSP, which is a number. But then the trick, right, 1 or 2 if you missed that obviously the concentration of OH, because there's 2 of them, is 2X, right? So solve for 2X, which is the concentration of OH. Turn it into a POH, turn it into a pH, right? And as you would expect, there's OH in solution, it's slightly basic. All right, so hopefully that all makes sense. All right, I'm going to put this up. Today's Wednesday. Try and look at this today and come to office hours tomorrow if you have questions. Okay, now of course, if you looked at that grade scheme and you think I made a mistake, tell me, I'll do a regrade. But remember, if I do a regrade and you get the same or a lower score, it's a 10% kind of off for the, for the regrade. Okay, so obviously if you spot a mistake, sure, ask for a regrade, but don't do it speculatively. Don't think, oh, I'll just try for more points. Don't do that, because you'll get less points. All right, so stop there. See you guys next time.